Okay, so we're gonna look at these really quickly, and you've all had trig. You understand that sine, cosine, and tangent are just ratios, right? That's all they are. For any angle within a triangle, within a right triangle, there is a ratio between the sides, and they're described as sine, cosine, and tangent. I used to have SOHCAHTOA up in my room. I need to get it back up in here. I don't think I'm allowed to paint on the walls just yet. Give it 15 years. That's actually how I remember them. If you watch me doing trig functions, you'll see me muttering under my breath, SOHCAHTOA. So sine is the ratio of the opposite side of any angle to the hypotenuse. So if we're looking at this angle, that is the opposite. And of course, you all know what the hypotenuse is. That's your hypotenuse right there. So sine is the length of the opposite over the length of the hypotenuse. Cosine is just the adjacent. And if I get rid of that, the adjacent, I very often, when we get into more complicated setups with multiple triangles, to keep myself from screwing up, this is one of those, I know there's a pothole and I'm finally smart enough to just walk down the other side of the street and not fall in it. I draw myself a line like that, and the line from the angle you're considering to the adjacent is going to be at a 90-degree angle. So CA is adjacent and hypotenuse, and again the hypotenuse is not changed. TOA is the only one that doesn't involve the hypotenuse. It's the one that we've been using to get direction on our resultants. And TOA, of course, if I can get this to cut selectively. Nope. Nope. There we go. TOA is the opposite over the adjacent. There are some trig functions that we'll get into a little bit later, but the one that we've been using so far for resultants is just tangent. And you've done this when we have a perpendicular vector and we can find the magnitude of the resultant with Pythagoras. We still have to find the heading of the resultant, and that's where tangent comes in. That's kind of what we've done so far. Where is your comfort level with that 0 to 5? 0, I don't know what language you're speaking. 5, give me the test now. Okay. Okay, we're between 3 and 5, pretty roundly. That's good. That's good. So here's the interesting conceptual thing, and it's really obvious once you look at it. If this resultant is made up of these other two pieces, these components, these component vectors, if we're given something that is in effect a resultant, we can work backwards and figure out what the component pieces were. So here, this is kind of what you're used to mentally. There are 3 pieces to this. There are 2 components, there's a resultant. If you have 2 of 3 pieces, you can always find the third, right? That's what we're used to in algebra and everything else. Well, now we're going to give you 1 piece of information and ask you to find the other 2. Can you do that? Obviously, or I wouldn't ask you to do it. How does this work? Well, for any vector quantity that has pieces of itself on the x and y axis, basically that's not aligned on the x or y axis, there are components of that motion, that velocity, that force on the x-axis and on the y-axis. So as long as we know the magnitude of that line, so let's say this is motion. Let's say that this is 25 meters. What we're now being asked to do is figure out what part of this is on the x And what part of this is on the y? Can you do it from what I've given you? No. I left out something. Angle. Because for any resultant vector, you have to have a heading. So there has to be some heading given. So this might be 23 degrees north of east. Well, if that's 23 degrees north of east, now do we have all the tools that we need to find? If we're calling this our delta x, or our, well, no, we would call it our displacement, and I'm not even going to abbreviate that for now. If that's our displacement, can we find within that displacement our delta x and our delta y? So we have to look at our trig functions, and here's what we know. For this angle, and we often call it theta, so for theta, it is true that the sine of theta is equal to what? So, opposite over hypotenuse. So it's opposite over, oops, can't draw an H, hypotenuse. And for that angle, the opposite is delta y. So the sine of theta is equal to delta y over what? Over our 25 meters, our total displacement. Now, can we solve that for delta y? Yeah, easily. So we now know that sine of theta times displacement equals delta y. Solve for delta y. Okay, so we have 9.76, etc. is your delta y. If you're sig figging 9.8, when we start putting those delta y and delta x displacements into larger equations, you'll want to preserve the entire number. So that's why the TI multi-views are really nice. If you're not using those, you're welcome to use anything you want. But those are really nice. Or compulsively write down all your numbers, which is a pain in the tuchus for most people. Okay, so can we find delta x? Can we find delta x without using a number that we computed? Yes. So we know that for that angle theta, the cosine of theta is equal to what? Adjacent over hypotenuse. So cosine of theta is then equal, because the adjacent angle to that to theta is delta x over the overall displacement. Cosine of theta times displacement equals delta x. So what's your raw number? 23.0126213. Good job. Okay. Will not let me make a decimal. Okay, 23, etc. Again, if we were sig figging for that as a final answer, it would just be 23 meters delta x. If we were putting that back into something else, we would preserve the whole number. Now, that displacement is a vector quantity. What's missing in our answers there? 9.8 meters what? Okay, so let's look at the delta y first. We said this was north of east, so we are looking at a compass rose situation. So this direction on the delta y is what? North. So that's 9.8 meters north is your delta y. What's your delta x? East. So let me clean that up. 23 meters east equals delta x. okay? When you are given that resultant and asked to break it up, you're pretty much always going to use sine and cosine. The wonderful part of this is that this can be used for anything that occurs that's got x and y components. Velocity, displacement, acceleration, force, any of them. So let's do 3B together, then I'm going to turn you loose on the 3B practice, and then I'm going to get the worksheets for you. So of course we have worksheets because, you know, physics. Okay, so this is from the sample problem 3B on page 93. Find the component velocities of a helicopter traveling at 95 kilometers per hour at an angle of 35 degrees to the ground. So we know that this angle theta is 35 degrees. And we know that this velocity, the magnitude of this resultant, is 95 kilometers per hour. On a test with a question like this, you are automatically getting a point for drawing that. That's a point right there. Labeling, I mean, and you don't have to draw a beautiful helicopter. I don't care if you generalize it to a dot. But there's an object, there's a vector, it's labeled with the magnitude, it's labeled with, you know, I see angle theta, and the next points that you're going to get is doing this, delta, or actually not delta x. Let's introduce a new idea here. So this is a velocity. We're now going to start talking about v sub x. That's the component of the velocity that exists on the x-axis. And, you guessed it, v sub y. And that's the component of the velocity that exists on the y-axis. I'll keep that in mind, though. So to find those components, so on a test problem, you've got, you know, a full points for your drawing. You're going to have the resultant labeled. You're going to have arrows for the x and y components. You're going to have the angle labeled. Like I said, I don't care if your helicopter is a blob. That's fine. To find v sub x, so let's use yet another color. Blue, okay? So we know that v sub x, there's a 90-degree angle there. X is going to be using what function? Adjacent. So which of our two functions that we're using, sine and cosine, uses adjacent? So, ka, toa. Cosine. Cosine uses adjacent. So we're going to start off with cosine of theta is equal to adjacent, which is v sub x, over our hypotenuse, which is our 95 km per hour. It's easy to solve this one. Easy. Cosine theta times 95 km per hour equals v sub x. Let's get a raw number. Who's got a raw number? Yes. 77.81944, etc. What are my units? Kilometers per hour. And we don't have any need here to change the units because we're just looking for component velocities. Km per hour. And my final sig figged answer would be 78. Yes. So v sub x equals 78 km per hour. What's my direction? Be careful. Well, we're not given north, south, east, and west. We're not even given left or right. I happen to draw it that way because that's my tendency. In a positive direction?
To the ground.
Well, it's along the ground. It's on your x-axis. So the v sub x is just 78 kilometers per hour, positive direction. You know, had that 95 been a negative 95. Okay, so on this, yeah, because there is no direction, you know, we would just say in a positive direction. Okay, let's do the delta y. All right, so looking at the delta y, which trig function are we going to be using? Sine, because it's opposite. And again, when we get into the bigger complicated triangles, I literally draw myself little arrows, because otherwise sometimes I just screw up. So we know that sine of theta is equal to v sub y over our resultant, which is 95 km per hour. I should mention, the other way to note that, and we should probably get right into the habit of doing it, and I was sloppy there. Sine of theta is equal to v sub y over v. You know, because that 95 kilometers per hour is their total velocity. V sub y is one component thereof. You know, if you're driving along a road with, you know, what your speedometer reads is your total velocity. We can analyze at any given point your x and y components of your velocity, but that is just your total velocity. Okay, so let's rearrange that to solve for v sub y. Sine theta times v equals v sub y. So the sine of 35 degrees times 95 km per hour is going to give us our v sub y. Somehow I moved that. Okay, you got a raw number? Okay. So our raw answer, 54.489, blah, 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 blah. Final sig fig would be 54 km per hour is our v sub y. This one has an obvious direction, which is up. The picture helps. Vertical up or vertical down?
But how do you know that this one is up?
Because the helicopter is flying at 35 degrees above the ground.
So couldn't the other one be to the horizon, like X?
Well, it is along the horizon, but we don't have a left or a right or a north or a south. So let's look at this, because this is one of the places where it does get confusing with the headings. So I want to examine this. Okay, so are we good with getting the magnitude? Now let's talk about the heading stuff, because this is where it does get a little bit thorny. Okay, so if I have the ground surface here and I have some object, I don't know what that is, doing this. The x component of its velocity, I'll do this in purple, is definitely along the ground. We know that. But if we don't have a north, south, east, you know, if we don't have that this thing is leaping into the air 35 degrees above the ground towards the east, then we don't know what direction it's traveling along the ground. We know it's traveling along the ground surface. You know, I'm traveling along the ground surface here. I happen to be heading west. I'm traveling along the ground surface here. I happen to be heading north. You know, so if we don't have any indication, all we can say is that that's a positive. Oh, I bet that recording was fuzzy. All we can say is that that's positive motion along the ground. Does that make sense?
Yeah, so when you would write it, like I had it originally positive about the horizon.
It would just be in a positive direction. Yeah, you could put in a positive direction along the horizon, but we already know it's on the x-axis.
And then for the other one I had vertical compared to the horizon, vertical on the horizon.
No, because let's say that we look at this situation and it's a little bit different. Let's shrink down our ground surface here. Let's say that there's a cliff. Let's say that this little person, being, object, whatever, instead of leaping up into the air, does this. So the component of their y is now this. Is that still vertical with regards to the horizon? Yes. But it's completely opposite that vertical. So for vertical displacements on the x-axis, if we're not, or on the y, good lord, for vertical displacements on the y-axis, if we don't have anything but above and below the ground, you have to specify up or down. So do you see how those are both vertical?
Yeah, I know that. I'm just saying, like, because you don't know, because this problem does say, but if it was meaning that if you could draw two different ways in the problem, vertical to the horizon would still be correct.
Not if it doesn't tell somebody if it's up or down.
Okay.
So there's a vast difference between, so a helicopter is flying at 35 above the ground, or, you know, we could have that same helicopter in the Grand Canyon flying below the horizon. And then the y component is down towards the earth. So it's still vertical,
Yeah.
but it's, you know, down towards the earth or up away from the earth. So yeah, you do still need to use up or down. As we come across more situations, and you've got lots of ones to practice on, you'll see the situations where, because we'll talk about the headings a lot, you'll see the situations where some things work and some things don't. So I think it'll become clearer as you do more of them. But yeah, it's the ones that have north, south, and east and west. North, south, east, and west are the easy ones. The ones that have, you know, up above the horizon always snag people, and the ones that have, you know, other kinds of motion snag them. Yes.
So, like, you had that line going this way
Mm-hmm.
on the horizon. That's positive. If it was going the other way, would it still be positive?
It would depend. So let's do an example. That's a great question. Let's do an example where it wouldn't be positive. So remember that positive and negative are conventions, and they're all made up. That should be reassuring. If you've got, you know, by convention, we mentally assign, because you guys have all been brainwashed in the Cartesian coordinate system, so have I. It's fine. It's not a bad kind of brainwashing. But we've had this grid superimposed on our brains. There is some sort of inborn, inwired tendency of people to draw motion in a particular direction. So let's actually go back to the helicopter and say, well, what if I, you know, why did I intuitively, instinctively draw it that direction? Well, this is given as a positive. So my brain says, oh, it's positive motion. It's got an x and y component. It goes in the first quadrant. What if we were told, and again, remember that the signs are all made up. We just use them to keep track of things. What if we were told that that same helicopter, we'll borrow the helicopter, and we'll just leave it flying, here, we'll make it fly upside down. That'll work. Sure, that'll work. Tell I'm not a pilot. What if we were told it had a velocity of negative 95 km per hour? Can something have a negative velocity? Sure. No. That's acceleration you're thinking of. Just move in a different direction. You know, if we're saying this is our 0 point, and anything in this direction is positive, anything in this direction is negative, if it has a negative direction, we don't run into these a whole lot. So, I mean, we're kind of doing what I'll call the corner cases. These are, you guys are raising great questions, but they're ones that I think as you go through more of the problems, they're not going to be such an issue. But if you were told something had a negative velocity, then you would start to think that, well, some component of that velocity has to be negative. If it's flying above the ground, we know the y, delta y has to be positive. You know, we know then that the delta x must be in a negative direction. In practical real-world terms, with displacements and velocities, in a situation like this, it doesn't really come up a lot. It will with forces, but we're not there yet. So, good questions. Probably once you dive into the problems, you're going to go, oh, okay, I see. Are we okay with leaving it there, or do people need more? Okay, so page 94, these are the 3B problems, all the odds, 1 through 7, and I will get you worksheets for additional practice.